Okay, there's four things that I want to talk about today. The first thing I want to do is define IoT, especially through the lens of the systems that I work on. The second thing, I think the principles of reactive systems really shine when applied to IoT. And I want to not just talk about these principles, but kind of highlight them in action by sharing two exemplary IoT systems. The first being the Tesla Energy Platform, and then followed by the Tesla Virtual Power Plant, which builds on top of the energy platform to control thousands of batteries on the power grid. And finally, I'll provide some speculation on where I think reactive systems and IoT are heading in the future from a platform perspective. And I think this will actually really tie in a lot of ideas that we've heard throughout the day so far. And before I begin, just a disclaimer that these are my personal opinions and experiences, and I'm not necessarily speaking on behalf of an employer, past or present. Okay, so to begin, what is IoT? So just because something's connected to the internet does not make it IoT. IoT first has to serve some kind of useful function. And even if something is connected to the internet and that information is exclusive to one entity, this is more machine-machine than it is IoT. IoT has to promise a level of interoperability and creating this kind of landscape of interconnected systems. So I like the definition of IoT that comes from this book, The Technical Foundations of IoT. It says that IoT must involve some form of sensing, control, and interaction. It must include local data collection, and I would add to this some ability to operate autonomously. There must be connectivity to the internet, hence Internet of Things. The cloud must enable novel services that would not be otherwise possible if the device wasn't connected to the internet. And it must serve a useful function, either through a user interface or some kind of application. So data collection alone is not IoT. And of course, it has to have an API for building interactive applications. And most importantly, IoT interoperates with other systems. So the fact that your refrigerator can display the weather is not IoT. Interoperability might be through software, and that's kind of the emphasis of this book. But I would add interoperating through things like markets or price signals, or even through devices independently sensing and maintaining the frequency of alternating current on the power grid. Okay. Next, I want to detail the Tesla Energy Platform. And this is an IoT platform that supports all of Tesla's energy products. And for residential customers, it supports things like vehicle charging, solar roof and retrofit solar, and the Powerwall battery. A Powerwall battery can provide backup power for a house for hours or days in the event of a grid outage. And we use this platform to deliver an integrated experience across all these products. Part of that customer experience is viewing the real-time performance of the system in the Tesla app. And customers can also control certain behaviors, such as prioritizing charging during low-cost times. Then for industrial customers, the software platform also supports products like PowerPack and Megapack for large-scale energy storage, as well as industrial-scale solar. And that platform also supports tools which allow industrial customers to monitor the performance of their system in real time, or look historically at performance over days, weeks, or even years. And finally, the platform supports the supercharging network, including availability and navigation. So these products for solar generation, energy storage, transportation, and charging, they all have an edge computing platform. And I'll just zoom in on that edge computing platform for a minute. It's used to interface with a diverse set of sensors and controllers. So these are things like inverters, buses, power stages. And it also provides local data storage, computation, and control, while also maintaining bidirectional streaming communication with the cloud over WebSocket. And this is so that it can regularly send measurements to the cloud, and so that it can also be commanded on demand from the cloud. Now, while this presentation is going to focus mainly on that cloud platform, I think that edge is ripe for innovation in the IoT space, especially through the lens of reactive systems. And I'll just mention a few things. And we can see some inspiration there too from Roland's talk earlier today. The foundation of this cloud platform is a linearly scalable WebSocket front end that handles connectivity and security. It is a Kafka cluster for ingesting large volumes of telemetry from millions of IoT devices. And this provides a few things. First is message durability on ingest. Second is decoupling of publishers and consumers. And it allows for sharing this telemetry across many downstream services. The platform also has a service for publish subscribe messaging, enabling bidirectional low latency the command and control of IoT devices. And these services are offered as a shared infrastructure on which to build higher order services. On the other side of the equation are these customer-facing applications that I just highlighted. And the APIs for energy products kind of break down into three broad domains. The first are APIs for querying historical telemetry alerts and events from devices, or streaming these as they happen. Second are APIs for describing assets and the relationships among these assets. And lastly, APIs for controlling energy devices like batteries. Now, there's way too many backing services to describe in detail, so I'll just provide a high-level understanding of each domain. And a challenge that you're going to see in each domain is the handling of real-time data at IoT scale. So imagine a battery in everyone's home. To support efficient historical queries and roll-ups of telemetry, so these would be queries like what was the power output over the past day for an individual device. We use InfluxDB, which is an open source purpose-built time series database. We maintain a large number of low latency streaming services for data transformation and ingestion. For some of these Kafka topics, the very first thing we do is create a canonical topic where data are already filtered and refined into strict types. And this removes the burden from each downstream service, and it also provides consistency across downstream consumers. A very unique challenge in this domain is the streaming real-time aggregation of telemetry from thousands of batteries. And this will be the focus of the second half of the presentation because it's the foundation for the virtual power plant. Now, product and customer information, of course, comes from many different business systems, and it's unworkable to have every microservice connect to every business system, some of which are not even designed to be internet facing or IoT scale. So the purpose of the asset management services, there's four different goals. One is to abstract and unify many different business systems into one consistent API. Two is to provide a consistent source of truth, especially when there are conflicting data. Three is to provide a kind of type system where applications can rely on devices of the same type, so like a battery or a charger having a consistent set of attributes. And four is to describe unique relationships among assets, like which devices can talk to each other and who can control them. We use Kafka to integrate changes here as they happen, or even to stream changes directly from IoT devices themselves. At scale, really, IoT devices are often the most reliable source of truth, self-reporting their own context in terms of configuration, state, and relationships. Now, a digital twin, which is some people also call this a device shadow, is the representation of a physical IoT device like a battery or a charger modeled virtually in software. And we do a lot of digital twin modeling to represent the current state of relationships and assets. We'll see a bit more of this later. And finally, there's these services for commanding and controlling IoT devices. So basically telling batteries to discharge at a given power set point for a specific duration is one example. And it includes the modeling the inherent uncertainty that comes with controlling these IoT devices over the internet. Now, Akka has been a really essential tool for us in building these services. Akka is a toolkit for distributed computing. I think most people at this conference are probably familiar with it. As far as actor model programming, actors are great for modeling state and for modeling individual entities like an individual battery. And then the runtime handles currency and distribution. And this is just a really fantastic model for IoT. And I'll provide some specific examples later on. Another essential part of the Akka toolkit for us is Reactive Streams component. So Akka Streams provides flow control, concurrency management, bounded resource constraints. And generally, the developer just writes functions, and then the Akka Streams itself handles the system dynamics by negotiating the rate of consumption. The Alpaca project is a way to interface reactive streams to a large number of services. This is what we use for interfacing with Kafka. And our primary programming language is Scala, largely because it's the first class way to use Akka, but we've also become very attached to the advantages of functional programming for building large, complex distributed systems. So those would be things like compile time safety, immutability, pure functions, composition, and modeling errors as data. The majority of our services run on Kubernetes, and Akka and Kubernetes, they really pair well together. Kubernetes can handle coarse-grained failures and scaling. So that'd be things like scaling pods up or down, or executing liveness probes and restarting failed pods with exponential backoff. And then Akka can handle fine-grained failures like circuit breaking or retrying an individual request, or it can model the state of entities, like the fact that a battery is offline or charging or discharging. And then we use Akka streams to handle the system dynamics in these message-based streaming systems. We generally use gRPC for APIs and protobuf for messages, taking advantages of the strict contracts and then code generation. So the takeaways from this platform. We embraced the principles of reactive systems from day one. We were kind of lucky to do this. It has produced incredibly robust, reliable, and effective systems. My background was in real-time systems for industrial automation for over a decade. And when I came across Akka and the reactive community, I was really excited to see kind of a formalization of the fundamentals that are so critical to these systems. Reactive streams are important for handling the dynamics and resource constraints, while also providing a rich general purpose API for streaming data. And then I mentioned this kind of theme of strict typing a few times. So rich types in Scala, strict schema with protobuf, as well as strict asset models for systems integration. And these constraints ultimately provide freedom and are the foundation for reliability in large-scale IoT systems. Okay, next I'll describe the Tesla virtual power plant, and this builds on top of the Tesla energy platform. So before I dig in, let's kind of review how the grid works, including the roles that batteries play. So supply and demand have to match in real time, or else the frequency deviates, which can damage infrastructure and lead to blackouts. The grid cannot store energy. So to put this in software terms, the grid has no persistence. And with traditional centralized generation, supply and demand supply can be turned up to match demand. And with only a small number of power plants, this is a relatively straightforward problem to maintain balance. But as we move to more renewable generation, there's becomes a few problems. First is reduced control. So generation can't easily be modulated to follow demand. In other words, you can't make the sun shine at night. There's uncertainty and rapid change. So it can suddenly become very windy, or it can suddenly become very cloudy, and this is hard to forecast. And then you also have distribution. There's many small generators behaving independently and sometimes autonomously. And you can see in these problems actually some parallels with some of the reactive systems concepts. So in a grid with a large amount of wind and solar generation, there might be variability in supply with times of high supply not aligned with high demand. And batteries can be used to charge during these surpluses and discharging during the deficits. And batteries can also respond very quickly, which is advantageous. Now, giant batteries that might be, say, the size of a typical natural gas peaker plant, they play an important role. But we can also take advantage of smaller batteries installed in individual homes. And these are already providing local value like backup and self-consumption of solar production. And then we can aggregate these smaller batteries into virtual power plants. I just want to make it clear that this is a feature that's only available to customers in specific programs. This isn't a feature that's necessarily available to all customers. As I just mentioned, the grid's not designed to interact with a bunch of small players. So we need to aggregate batteries to look like a more traditional asset, one of those natural gas peaker plants. And a typical way to do this is through hierarchical aggregations, where the hierarchy is a virtual representation in cloud software. The first level is that digital twin that I mentioned earlier, representing an individual site. So that's a house with a battery. And the next level might be organized by electrical topology, like a substation, or by geography, like a county. And then the next level can again be a physical grouping, like an electrical interconnection, or it might be logical, like sites with a battery and solar, and sites with only a battery that we want to model or control differently. And these sites come together to form the top level aggregate of the virtual power plant. And this means that we can query an aggregation of thousands of batteries as fast as we can query a single battery, and then use this to inform a global optimization. Now, it's easy to think of the virtual power plant as kind of uniform, but reality is a little more like this. There's a diversity of installations and home loads. Some homes have one battery, some have two or three. The batteries are also not all fully charged. Some might be half full or close to empty, depending on the home loads or the time of day or how much solar production occurred in that day. And also this uncertainty of communicating with these sites over the internet, as some sites may be temporarily offline. And then finally, there's the asset management problem of new sites always coming online, firmware being non-uniform in terms of its capabilities across a fleet, or hardware being upgraded and replaced over time. So it's critical to provide a representation of this uncertainty in the data model as well as in the business logic. So we want to be able to say things like there's 10 megawatt hours of energy, but only 95% of the sites we expect to be in the aggregate are actually reporting. So kind of communicate that uncertainty, because it's really only the consumer of that data that can decide how to interpret the uncertainty based on local context. So one way we manage this uncertainty is with a site abstraction. So even if sites are heterogeneous, the site level telemetry provides a consistent software abstraction. And then another way is to aggregate sites into a virtual power plant. And this is actually quite a difficult engineering challenge, which is a combination of streaming telemetry and asset modeling. So for modeling each site in software, the so-called digital twin, we represent each site with an actor. And the actor manages state, like the latest reported telemetry of the battery, and executes a state machine, changing its behavior if the site is offline or online or telemetry is delayed. The programmer just models a site in an actor, and then the runtime handles scaling that to thousands of sites. And this is just a really powerful abstraction for IoT. And we generally never worry about things like threads or locks or concurrency bugs. The higher level aggregations are also represented by actors, and then actors maintain their relationships to other actors, describing the physical or logical aggregation. And telemetry is aggregated by messaging up the hierarchy in near real time. And how real time the aggregate is really just a trade-off between messaging volume and latency. And then we can query at any node in hierarchy to know the aggregation at that location. Now, the services that perform this real-time hierarchical aggregation run in an Akka cluster. And Akka clustering allows pods in different roles to communicate with each other transparently. So the first role is a set of linearly scalable pods that stream data off Kafka, and they use Akka streams for back pressure, bounded resource constraints, low latency stream processing. And then next is a set of pods running the actors that represent the sites or the higher level aggregations. And when the stream processor reads a message for a particular site, it just sends the message to the actor for that site identifier. And it doesn't matter where in the cluster that actor is running, the Akka runtime will transparently handle the delivery of that message. This is called location transparency. And then these site actors message with their parents in a similar manner all the way up the hierarchy. Then there's also API pods that can serve client requests for site or aggregate telemetry by querying into the cluster in this same location transparent way. And it's this full collection of services that provide the in-memory, near real-time aggregation of telemetry for thousands of batteries. And it's also an architecture that provides great flexibility and reliability, especially when paired with Kubernetes to manage the pods, as the actors are just kind of running on this like virtual substrate of compute that the developer doesn't have to worry about. And an individual pod can fail or be restarted, and the actors on that pod will simply migrate to another until it recovers. Or the cluster can be scaled up or down, and the actors will rebalance across the cluster automatically. Actors can recover their state in these situations using Akka persistence, but we don't actually use it in this instance because the batteries communicate so often that the actor can just rediscover its relationships when it receives the next message within a few seconds. Finally, let's look at how the batteries are actually controlled. So there's two primary methods of control. The first is direct control. So that's taking past measurements, forecasting, and then deciding how many megawatts to discharge. And to give a sense of scale, this might be enough megawatts to offset the need to build a new natural gas peaker plant. Or we may control only a subset, depending on the objective. So the control service dynamically resolves the individual sites under the target by querying the asset service. And this is because the sites can change over time. So there's new sites, or the virtual hierarchy is modified, or the properties of an individual site change. And then the control service queries the battery telemetry at every site, so potentially thousands of sites, using the in-memory aggregation that I just discussed. And this is to decide how to discharge each battery. There's no point discharging a battery that's kind of close to empty. You can think of this kind of like a database query planner. The control surface then sends a message to each site with a discharge set point and a time frame, and it'll keep retrying until it gets an acknowledgement that the message has been received. Because these logical aggregations of batteries are so large, we stream over these huge collections of using Akka streams these 3 steps. So resolve the sites, read all of the telemetry, and then send all the control set points. And this actually runs in a closed loop every few minutes. Another way we can control is to take advantage of the edge computing platform. So for example, we can distribute time series forecasts for energy prices or weather and run the optimization at the edge. And one advantage of the distributed optimization is scalability. We don't have to solve a huge optimization over all sites. And the other advantage, which also applies to direct control, is resilience to the inevitable intermittency in communication. So if sites go offline for short amounts of time, they can operate autonomously. And if sites go offline for longer, they can revert to purely local optimization, which still provides value to the customer. So these huge aggregations demand different APIs and data processing patterns. You can't just use typical CRUD APIs. They need streaming semantics for processing huge collections with low latency, bounded resource constraints. And then they also need runtimes for modeling stateful entities that support location transparent messaging, concurrency, scaling, resilience. Uncertainty is inherent in these IoT systems and must embrace this reality in the data model, in the business logic, even in the customer experience, rather than trying to escape it. And what we really need for building these services for IoT is a toolkit for distributed computing. So for us, that's been Akka. For others, that might be Erlang OTP or Microsoft or Leans. And I think we're now starting to see the evolution of stateful serverless platforms to support these same building blocks. Which leads into the final part of the presentation. I'll just provide some personal opinions and speculation on what I think defines a state-of-the-art IoT platform and where I think the industry is trending, especially in terms of platforms. So what is a state-of-the-art IoT platform? So if you look at the platform that I presented, or you look at the similar IoT platform from Microsoft, there's one from Amazon, another one from Google. There's a lot of commonalities across these. The first is a distributed journal for events and facts. So this offers a decoupling of publishers and consumers and a way of sharing events reliably among services. They all have flexible message routing to deliver the right message to the right services and provide loose coupling. They all have publish subscribe messaging for low latency command and control. They all have a time series database for very low latency queries over time for individual devices, as well as various databases for describing relationships among devices and including how those relationships change over time. They all have platforms for stream processing to react to events in near real time, and they all have some kind of data lake or batch processing system. I think there was an impression a few years ago that Lambda architecture is dead or whatever, but I think it's alive and well, with some applications being best served in streaming context and other ones, some questions you can really just only answer in a batch context. I think they're trending towards an edge computing platform. And I think the more you view the edge as a platform, embracing reactive principles there and APIs at the edge, rather than just connecting each device independently with an API to the cloud, I think the bigger the advantages. And so for example, some IoT platforms are evolving to support flexibly moving compute or configuration from the cloud down to the edge or in the reverse direction. Asset management is the hardest problem in IoT, and a state-of-the-art platform has to have facilities for first-class asset management, things like PKI, firmware updates, desired state configuration of devices at huge scale. And lastly, there's some facility to model individual entities, so these digital twins that are IoT devices, transactions, customers, those kind of things. And this is really essential for building responsive, interconnected applications that go way beyond just data collection and query. Finally, I want to speculate on where I think the industry is heading, and I'll just there's a lot of academic research I think is interesting, but I'll just highlight a few trends that are actually in the public domain that are catching my attention. So first is Cloud State as a general purpose serverless platform for modeling stateful entities through event sourcing. There's a presentation later today on this by James. I think the new stateful functions in Flink for incorporating stateful entities with streaming data is really interesting. If you check out this blog post is actually inspired by the virtual power plant example that I just described. And it implements a similar approach to hierarchical monitoring in a data center. So you can contrast those two approaches. I hosted a QCon track about a year ago. I really love this talk by Chris Gillum on Azure Durable Functions for modeling individual entities, as well as modeling stateful workflows, because so often things are related and need to be expressed in a stateful workflow. Cloudflare recently had a beta of durable objects for workers. So this is kind of an actor-like programming model that provides isolation, durability, and addressability no matter where in the world an object is running. And I also enjoyed this paper from Microsoft Research, which is basically applying empirical models to improve the performance of serverless workloads on top of Azure. So I think kind of combining those ideas, I think this is where platforms and IoT are heading. Undoubtedly, the future is serverless. Kubernetes is great, but kind of orchestrating boxes of software is a way for us to get from A to B, kind of a temporary stop along the way to pure serverless, where we don't have to run or maintain the infrastructure. Serverless programming models for handling state will continue to improve and become the norm. I think modeling individual stateful entities, so devices, transactions, customers, will really need to be a first-class part of the platform. And this will allow the platform to handle scaling, distribution, failure, some of those things that we're taking advantage of Akka for. And I think this perhaps allows even different hardware architectures that aren't so focused on boxes of software like VMs and containers. I think streams will emerge as the way to compose entities and workflows and control the execution dynamics. And I think the stream will actually kind of become the call stack of a serverless distributed world. Computation will become itinerant. And what I mean by this is that it will be able to move around from place to place, like moving computation from cloud to edge. And to make this happen, we can't imperatively tell the computing platform what to do. We'll need to use declarative computing models. I think functional programming will be the natural way to do this with the advantages of composition as well as input-output models and pure functions. And if you look at functions as a service, Lambda type things, it only supports specific languages. And for some of those, you actually deploy an executable targeting a specific platform. I think there's huge opportunity to define kind of a platform for serverless and IoT where you ship bytecode for functions or for entities. And this will allow moving code from cloud to edge, flexibly, those kind of things, or from one architecture to another. Maybe the cloud provider has a new ARM processor and they want to try it out. So I kind of think of this as like, a .NET-like platform for all of serverless compute. I think this is one of the reasons you see some excitement around WebAssembly. And finally, I think we'll take empirical approaches to improving cost, latency, data locality, throughput, these kind of things. And I think the operation of the platform itself is going to look a lot more like process engineering, managing dynamics, state, operational objectives. So like, for example, if we were kind of shipping that bytecode, you could imagine the cloud provider running a shadow service where they're actually evaluating throughput or cost of the service and kind of borrowing approaches for continuous improvement from the process industries in order to serve customers better. And I think that it'll be these things coming together that'll define reactive systems in the future for IoT. So those are the 4 topics I wanted to cover. I'll just end with a quote. It's difficult to predict the many applications of IoT once it has reached the stage of ubiquitous expansion. And I think IoT will really be successful when it kind of melts into the background and we don't even notice the novelty of something being connected to the internet. And I believe that the evolution of serverless computing platforms and the influence of reactive systems will play an important role in making this happen.